All right. Uh, these are the lesson 4.4 factoring polynomials notes. I'm going to try to keep it as quick and short as I can, but I also know that factoring is something that students tend to struggle with. We looked at earlier on, or in earlier chapters, actually factoring really quadratic stuff, quadratic polynomials, second degree stuff. Here, obviously in a chapter on just higher degree polynomials, we're extending factoring to no longer just second degree stuff, but we're going to rely on a lot of those concepts that we learned from earlier on in the year. So let's take a second here. You can kind of see what's coming here. I gotta review factoring, just quadratic factoring, and then we'll tie that hopefully into some those skills into some stuff that with some higher degree. So like I said, I'm going to try to keep it short, but I understand that this is probably going to be a little bit longer of a video. I guess it is what it is. I guess it can be shorter if you're solid and you feel good about factoring, or you felt good about factoring quadratic functions and polynomials. This isn't too much of an extension beyond that, but let's do it. Let's do the factoring review. So second degree stuff. So this is all stuff we've done before. If you don't remember this and you're like, well, what's going on here? Make sure you're adding this to your notes, not just watching me do it. I know how to do it. It's that if you're struggling a little bit, you'd make sure that you have these examples, because like I said, we're going to extend these to higher degree polynomials. So here we go, one at a time. You know what? I'm going to just bring this down to give us a little bit more room. So just in class, it makes a little more sense to have these all, because you'd be laying them all out. Oh no, I was hoping to bring this whole thing down. Let's do this just to get us a little space to work. So first one here. This is what I would call your traditional factoring. It's so we start to kind of look at how many terms are we talking about. So I've got a 1, 2, 3 terms. So I see 3 terms. I got a second degree. My initial thought here is, when I have this, especially when this is a 1 in front there, is I'm looking for 2 numbers that multiply to 108, this C term here. So multiply to 108, that add up to this B term right here. And 108's, I mean, it's got some factors in it, definitely. So I'm going to start to look at. I've got my calculator in front of me, and I'm basically dividing. I'm starting with the 108. 108 divided by, let's see, 8. I don't know. I'm just grabbing a number. Nope, doesn't work. 108 divided by 4. Okay, 4 and 27. So let's just say I think that's it. 4 times 27 is 108. The problem is there, 4 plus 27. Like, I'm not going to get it to work. All right, let's try 6. 108 divided by 6. Oh, 6 and 18. So this at least gives me a process, though, like something to follow. All right, 6. So I'm seeing, so I just did 108 divided by 6. I got 18. So 6 and 18. So now I'm thinking, all right, 6, 18. It's close. I mean, it adds up to 24. I tried 8. Let's try 9. 108 divided by 9. So and it hits again. So 9 times 12. All right, 9 times 12 is 108. 9 plus 12 is 21. I think I found my combination. So that's the idea. Obviously, the bigger the number this gets, the more this process could, the tougher this process could be. But once I come up with that combination, okay, 9 times 12 is 108. 9 plus 12, whoops, I wrote 21. 12. 9 plus 12 is 21. As long as this is a 1 here, which is kind of the big deal, and it is, I mean, it's 1, I'm ready to say, all right, we're ready to factor. I'm using these 2 numbers, and I'm writing this as factored. X plus 9, I just use this because it's a positive 9, so I write plus 9, and then I use this because it's a positive 12. X plus 12, and we are factored there. So that's what I would call your traditional factoring. 2 numbers that multiply to C, that add up to B. We can use that when this is a 1. Okay. All right, let's start over here. Number 2. I'm still counting terms, I guess. So it's 3 terms. I can't factor anything out. That's another thing that we would look to do right away. Can I undistribute anything? Let's see, 10, 19, 7. These aren't divisible by anything. other than 1. So I can't take anything out of these terms. So this is 1 now that I have to look at. I'm going to follow a similar process here. I'm looking for two numbers that multiply to not 7, but 7D. Okay, the A, I got to account for this 10 right here. So the 10 and the 7, that's where the 70 came from. And those same two numbers, we still want to add up to the negative 19. So use the negative there. That's with the 19. So, and again, I'm trying to come up with these combinations here. I'm going to double check it quick on my phone. Or my calculator, sorry. 14 times 5 is 70. 14 and 5. 14 and 5. Okay, so I think that's right. 14 times 5 is 70. 14 plus 5 is positive 19. I just got to mess with the signs a little bit. And in this case, I think making them both negative, that's a negative times a negative is a negative plus a negative, negative 14 plus. Okay, so there we go. There's our combination. Now the difference is, or at least the first, well, there's already been some differences. But the next big difference is I can't just go x minus 14, x plus 5, or x minus 5 because we got to, this is not a 1 here. So here's kind of the next move is, all right, start rewriting this. Start right here, 10x squared. And then instead of this 19x, let's break that 19 into these two numbers. So negative 14x and then negative 5x plus 7. So I've essentially recopied the original 10x squared and the plus 7, but I've just broken that negative 19 into those two numbers that we spent a little bit of time coming up with. All right, from here, group, and this will come up later, so it's a good review for us regardless. Group these first two terms together and these last two terms together. So you put a little parentheses around them, that's what I mean by group. And then we look, let's focus on the first two. Take out whatever we can take out of both of these. We should, so I'm going to undistribute what, like through division. I can definitely take out, it should always work out this way, where they have an x to give. Because we kind of created, there's going to be an x squared and an x always. And then numbers wise, let's see, they're both, I mean, nothing crazy. They're both divisible by 2, it looks like. Okay, so I've taken out a 2x out of both of these through division. So what would be left? There'd be a 5x here, right? So I'm kind of taking a 2x out of that. There'd have to be a 5x. If I were to redistribute, I'd get 10x squared. And then this is just going to have to be a solo just 7. So 2x times negative 7 is negative 14x. Awesome. All right, so I've taken out as much, I've factored out as much as I could. It's written out here right now. For the second one here, we almost like predetermine, hey, you know what? We want to make this interior, what's in the parentheses, identical. Like it has to work this way. Whatever we came up with, so I finished this process here, and whatever was in the parentheses, I rewrite here, 5x minus 7. And now I'm looking here and here, and I'm asking myself, okay, are these identical? And it's close, but they're not identical, right? So I ask myself, okay, what do I have to take out of these terms to make this look like this? And it's close. Again, it's through division. If I just divide out a negative 1, I basically need to change the sign on both of these, right? So if I were to just quick check redistribute, negative 5x plus 7, sure, okay. So then I actually am ready to kind of put it together now. Whatever's on the outside here and here, so you should end up with something in front here, whether it's 1 or whatever, I guess at minimum it would be an x. And then same thing here. It could be, if this was identical to this, then I'd say, all right, I factored out a 1, nothing changed. Okay, fine, a 1 came out. So you should always end up with something outside here and here. You take that, what I'm calling the outside stuff, and stick it together in its own binomial. So 2x, so I've taken this 2x, this negative 1, and put it together. And then I just use one of these, 5x minus 7 as its own single binomial. And now we are officially factored. All right, so I mean significantly more work in the sense that we got to come up with this combination, but then I got to split it into 4 terms, and I got to factor out, and I got to put that stuff together. So that's definitely one of the longer types of factoring that we've seen, but there's not really any way around it. All right, so those are a couple of our 3-term factors. One more here. Let's do that same thing I did where I spaced this out a little bit. Um, so for one here, it's still three term. It is a special pattern one. I don't think you have to necessarily recognize that. So I look at, on one, two, three terms. Okay, sweet. I can handle that. If I don't even recognize that it's special pattern, I would just, how would I start this process? I'd recognize and say, hey, that's a one, sweet. We like those. I need two numbers that multiply to 144 that add up to negative 24. And here's what, kind of makes it a special pattern one is those numbers. I see 144 and I think 12 times 12. To me that just jumps out as a perfect square. So 12 and 12 is 144. 12 plus 12 is 24. If I make them both negative, I can make the signs work. So as I go to finish it, and again, because it's a 1, this is so much shorter and sweeter. X minus 12, x minus 12. It's the same number twice. So we would want to shorten this up and just call it x minus 12 squared as far as being factored. So remember, that's what we called a perfect square trinomial that came up in our complete the square section in the previous chapter, chapter 3. So that's where we had seen that before. It is pattern based, but I know I said it even at the time. If we don't catch that, it's going to show up factored just through our normal, quote unquote, normal process. All right. So there's just a quick look at one that is technically a special pattern, although we don't necessarily have to recognize it. This definitely is something we have to recognize. Like this isn't, you could try to factor this and you would actually probably be okay if you rewrote this as 4x squared plus 0x minus 25 and then tried to go like a times c, and you're making way more work than you have to. Okay, so this is our first one we're seeing that is, all right, hey, it's two terms. That stands out to me as weird. Like that's, what the heck, two terms? How do I handle that? So the first thing I would look for is this subtraction. And it is, okay, subtraction, difference. Remember, that's subtraction means difference. And if it is subtraction, I'm not saying this automatically means this, but if it is subtraction, I'm saying, okay, yep, step one, it's subtraction. Is this first term a perfect square? So 4 is a perfect square, x squared is a perfect square, okay? Is this a perfect square? 25, yeah, 5 times 5. So this is what we call our difference of squares pattern. And again, I'm putting a little bit more emphasis on it because I know it's going to come up later. Difference of squares pattern. It's exactly that. It's a pattern where it's going to factor. I'm going to jump right from this to factored, as long as I recognize that it's that type of pattern. It's the square root of the first term. So square root of 4 is 2. Square root of x squared is x. And I'm basically reserving that in both spots. So 2x, 2x. Square root of 25 is 5, 5. And then I need to remember that I need one of each, a positive 5 and a negative 5. But that's one that, again, if we practice a little bit and we see it and we catch it, there's not really any work. There's nothing to really, that's how that's going to factor every time. Square root of this, square root of that. You need two of them. There needs a positive and a negative one. All right. Last one, and it's a good one to, I guess, to finish with because it actually kind of leads into the next section. But it's another two terms, so it jumps out at me as, all right, this one's weird, right? It's not my traditional factoring. It's two terms, but then I see, hey, that's not subtraction. So never mind. It's not difference of squares. It's actually probably the first thing we should always look to do on anything that we're being asked to factor is, can I take anything out? Can I factor out? Kind of divide out anything common? And the answer is yes, right? This 8 and this 20 are both divisible by 4. And actually the x squared and x are both divisible by x. So we're going to do that. You can almost put parentheses around this and say, hey, you know what? I'm going to take something out of both of these. So then the parentheses, let's clear that here. The parentheses will kind of end up staying put. I just need a little bit of room to write what's on the outside. So the parentheses are going to kind of stay put. The plus can stay there. That's fine. What did we say we were going to divide out? The common factor between 8 and 20 is 4. And then they each have an x to give. So we can take out an x. And then I ask myself, okay, what has to still be here? What has to remain? There has to be a 2 and an x, because 4 times 2 is 8, x times x is x squared. What has to be over here? 5. 4 times 5 is 20, 20x. Okay, so that's more of an example of factor out. Now we've seen combinations where maybe I factor something out and then we're left with something else that can be factored. Actually, I don't know if we've seen it yet. That's what we're gonna see, is maybe some combinations of some of these. So that's part of it. So there's just a straight up quadratic factoring review stuff we did earlier. I guess at this point, if you're like, oh hey, you know what, I got all that, you're like, darn it, I wasted my time. I think you'll probably at least be a little bit better off for seeing and hearing some of that stuff. Okay. All right, so let's get to some of the newer stuff. One of the first things we're going to see is like a direction that says completely factor the polynomial. And I wish I could give you like a, hey, this is what it always means to be completely factored. I mean, I guess I can give you a little bit of completely factored means that you can basically look at each, each factor and say that, hey, we can't break this down any further. All right, x plus 1 can't be broken down into any more things that multiply together to get that. Nothing, this can't be broken down any further. Unfortunately, it's not as easy as always saying, look, hey, make everything first degree, right? First, 2 to the first power, x to the first power, 1 to the first power. Like, I don't see any exponents in this first one, and I made it way more cluttered than it already was by putting all that stuff in there. But like, everything's first degree. I don't see any exponents. And you're like, sweet, that's what it always means to completely factor. But the problem is here, if I look at this next one, this is also completely factored, except I see squares, I see second powers. You're like, what? Well, how do I know that that's not completely factored? It's just going to come through practicing and seeing. Here's an example of something that's not completely factored. You say, what the heck? These are so close. This one has more exponents than this one. Why can this one be factored and this one not? Here's that difference of squares pattern, right? So I'm looking at each factor. This is done. Anytime you just have a number next to, just a single x, whether it's to the second power, fifth power, 20th power, as long as there's no addition, subtraction, I don't really have to worry about anything else being factored any further. So this 3x, the 5x squared, done. That's always going to be factored. But anytime I have like a polynomial with, which polynomial means separated by addition, subtraction, I got to kind of at least ask myself, can I break this down further? And I know I already said it. This is that difference of perfect squares pattern. So this x squared minus 4 can be broken down into what? X plus 2, x minus 2. We just got done going through that difference of squares pattern. This 3x we said was done, so it's kind of just trailing along. So now I could say, hey, yes, this right here, this is completely factored. If you ever do get it down to where everything's first degree, then sure, yeah, everything, then that's done. And that's kind of how we ended up here. But I just wanted to at least to see this one, to see like, hey, that's not, 3's not a perfect square. Like, that can't be factored. This is okay to leave as completely factored. Okay. And like I said, that's just going to take repetition and seeing and practicing and doing some of that. Okay. So I've kind of broken it down here a little bit in some different types. This first one, there's like a common theme for each one of these. And again, I'll probably have to spread these out because I'll just do it all at once. In class, we would have been doing them on the board. Whoops, maybe if I can write here or not. All three of these have a kind of a common theme in that, I was hoping I could click, that they all have something that can be factored out of them and then continue to factor again. So there's kind of two factorings going on. So let's just kind of go through them and see what happens. All right. So the directions are basically factor the polynomial completely. Okay. We just talked about that. So I see this. Hey, I'm counting terms again. 3 terms. All right. So I'm kind of thinking traditional, but here's the problem. That traditional factoring only works when that was quadratic. Right now it's third degree. But I'm also recognizing, hey, there's a y here, there's y's here, there's y's here. Let's take a y, at least take a y away from each one of these. So factor out a y. So y kind of comes to the outside. What does that leave us with? All right, I'm basically taking a y away from each one of these. All right, so I've divided out a y. I didn't cancel it. I didn't erase it. I can't do that. I'm just factoring it. So step one, I guess if I want to call it like, hey, step one, we factored out. That's supposed to be a number 1. And then I look at what's left and say, can this be continued to factored? And now this is done. We said anything kind of sitting by itself is already factored. Now I'm looking at what's inside the parentheses and seeing, hey, that's a 3-termer. It's a 1 out front there. That's kind of nice. Can I come up with two numbers that multiply to -12 that add up to -4? So I'm running through, let's see, 6 and 2. I kind of like that. 6 and 2. Can I make that work? 6 and 2. I think just making the 6 negatives. Yeah, negative, negative. Okay. So then this can, so the y is done. We said I boxed it because it was already done. But then now this is getting broken into, I'm ready to go to it, y minus 6, and then y plus 2. And now, again, like we said before, if everything happens to go down to just first degree, no exponents left, then yeah, for sure, we're done. All right, so that's kind of the common theme for these first couple is factor out, and then whatever's left, factor it. All right, so let's take a look here. Same idea. I see, I'm counting terms, 3 terms. Okay, so I'm thinking traditional. Right, that's pretty much our only way that we know of to take care of a 3-termer is kind of that quote-unquote traditional or normal factoring. I want to make life easy on myself, though. I see a 3rd degree. I don't know what to do unless it's 2nd degree, so I'm guessing we're going to have to be able to take an x away from everything. And conveniently, all 3 of these numbers are divisible by 3. So let's take out as much as possible. If I take out not only just an x, but a 3x, what does that leave us here? It leaves us with an x squared. It leaves us with a 10x, and then it leaves us with a 25 here. All right, you do a quick check. I always say it. 3x to the 3rd, distribute 30x squared, and then 75x. Okay, this is done. 3x just sitting solo. So now I'm focusing on what's left here. Can this get factored? And to be honest, I have no idea. Maybe it can, maybe it can't. I'm not saying this is always going to be factorable. How do I know if it's factorable? Can I come up with 2 numbers that multiply to 25 that add up to 10? So I'm thinking, and again, 25 kind of jumps out at us, hopefully, as, yeah, 5 times 5 is 25, 5 plus 5 is 10. So this is one of those perfect square trinomials that's going to go x plus 5. And if you see this here, I mean, we'll do it in 2 steps, x plus 5. And then I had that 3x from original. I mean, I still want you to, if you get here, I'd say you're getting really good and you're starting to see it. Let's put these together. 3x times x plus 5 squared. So it's a good example, at least, to see one that, hey, there is a 2nd degree, even though you could argue in this step there weren't any. We just kind of put those 2 because they were the same together. This is where we want to get. We say, hey, we're factored completely. I know there's a 2nd degree. That's fine. You know, that x plus 5, there's just 2 of them. All right. So factor out and then factor what's left. C, already jumping out is weird, right? It's 2 terms. What the heck? How do we handle 2 terms? So I see this as still there's g's here. There's g's here. There's lots of g's actually. And then both this 5 and this 80, they're at least, I know, divisible by 5. So let's take out a 5. Let's take out as many g's as the smallest will allow. So I'm going to take out 3 total g's. What does that leave us here? This whole 5 came out. Most of the g's, there's still 2 of them left, right, through division. I kind of took them away. The state subtraction, and then all the g's here went out. But 80 divided by 5 is 16. So then, what's the common theme? We said we factor out to start, and then we look to see, all right, it's still a 2-termer here. What's going on? There's subtraction, that's difference, perfect square, perfect square. We'll see this one so many times, it'll just become like old habit. Oh yeah, difference of squares, no problem. I can finish this. 5g to the 3rd, we said anything just kind of with no addition, subtraction is just done. And then how do we finish this? It's g plus 4, g minus 4, right? The square root of each. Make sure you save a plus and a minus for each one, and that's where we end up. All right, so factor out, factor what's left using traditional methods. All right, let's keep her moving here. We're doing okay. You can see there's still a lot to go, though. New special pattern, right? So really the only, let's just call difference of squares the only special pattern that we have to kind of recognize. This is our next one. So now this is something new for us. Special pattern. It works the nice, I guess maybe the good. The downfall is it works for both sum or difference, and we're looking for cubes. So no longer perfect squares, but perfect cubes. What are perfect cubes? 1 times 1 times 1. That's a perfect cube. 2 times 2 times 2, which is 8. 3 times 3 times 3, which is 27. 4 times 4 times 4. Let's see. I'm second guessing myself. 64. 5 times 5 times 5. 5 times 5 is 25. 5 times 25 is 125. So it's a different set of numbers. They're still, they still kind of work the same way as perfect squares, except there's another one. So 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3. Those are examples of numbers that are perfect cubes. So basically what we're looking for, I think this is fairly complicated. Set up your notes where you have special, just call it sum or difference of cubes. Okay. And the nice part is it works the same whether it is subtraction or addition. There's a pattern that goes with it. Okay, I think maybe this makes the A's and the B's make things a little complicated. We'll maybe do 2 examples here to maybe clarify it, but sum or difference of cubes would be your heading here. This one's a little bit simpler. It's just easier to recognize. Hey, x times x times x, that's a perfect cube. 2 times 2 times 2. Sum or difference doesn't matter. How this would factor, maybe this one's at least worth having. And again, I know it's tight. We're just going to kind of write it. But how it works is, all right, it's the cube root of this first one. So x times x times x, what's the cube root of x to the third power? It's x. That goes right here. What's the cube root of this one? 2. 2 times 2 times 2 times 2 goes right here. Okay, so the cube root of each number, and I kind of preset this up without really talking about, there's going to be a binomial and a trinomial. It's just that's the way it's going to work out. And then I've got 3 more spots reserved, right? This is going to be a trinomial, three spots. So this first spot is reserved for this squared. Okay, so hopefully that's easy enough. X squared is x squared. This last spot here is reserved for this squared, whatever this number is. So 2 squared is 4. The middle one, okay, I got 1 more spot reserved right here. It's this times this, so x times 2, which is 2x. Okay, so that's kind of how we fill it in. Again, we'll do 2 more of them here so you can kind of see. And then the last part is filling in the signs. Here's kind of the note on that. We're going to use what's called it's kind of crumbly written there. A mnemonic device. SOAP. Let's write it like this. And this is how we figure the signs out. Same, opposite, always, positive. So what that means is you use the same sign here as whatever the original was, same. Use the opposite right here, and then the last spot is always positive. I know that's really small, and there's a couple other examples here. I think these ones are a little bit more complex than the ones that I'll ask you to do, so that's why I said let's practice a couple here. Some sum or difference of cubes patterns. It's still, I think it jumps out at least as like, hey, this is weird. It's 2 numbers. And right now, the only way we know how to handle 2-term factoring is either factor out. Well, I can't factor anything out of this. Or difference of squares. Well, it's not a perfect square. That's not a perfect square. So this is kind of the third option then. It's difference of perfect cube. So here we go. I would jump right to just setting it up as, a small little, like binomial, leave space for 2 things, and then kind of a longer space for 1, 2, 3 things, a trinomial. Okay, so there's a little bit of like just a format of like, that's just how this is going to factor. And then I ask myself, okay, what's the cube root of this? Z times Z times Z. So Z, that goes here. What's the cube root of this? 5 times 5 times 5. The cube root of 125 is 5. Fill this one in. So you just kind of go in order. The first thing listed here, you square it. It goes right here, Z squared. The last thing listed gets squared and goes right here, so 25. And then this middle spot is reserved for just this times this. 5 times Z is 5Z. We'll look at the next one. There's a little bit more going on, but Okay. So then the last part, here's that SOAP, S-O-A-P, where the first symbol, the first operation is going to be the same as I see in the original. The second one's going to be opposite. So the opposite of negative is positive. And then the last one is always positive. And that's, I mean, other than, I don't like these lines here, but other than this being here, that's how that would factor. The other kind of nice part, if we can get here, I don't have to check anymore. Like I don't, you might say, well, can't this be factored? And that's a really good, fair question. But if we've done it right, we're not going to be able to come up with two numbers that multiply to 25 that add up to 5. Right? There's just not a combination that's going to work. So I don't have to worry about that when I'm doing a sum or difference of cubes pattern. So it's kind of, I guess, a silver lining there is usually just factor it kind of that one way and you're done. I kind of ran out of space here, but here we go. Part B, we're starting to look at, well, Mr. Pro, you just wrote these perfect cubes, and 81, you jumped over 81. 81's not on that perfect cube list. Neither was 192. And I'm also looking at, well, what the heck? There's a fourth power here. That's not a perfect cube. So this is one we're going to have to take out as much as we can. Like this is a factor out to start. So when I take out, so I'm recognizing I might have to check on my calculator, like, hey, what is 81 divided by? I got to see what can I take out of these two numbers? They're both pretty big, right? So what if I take out a 3? I take out a 3, and then I also recognize, hey, there's a y to give on both of these. So if I take out a 3y, what are we left with? We're going to be left with 27 y to the third, right? We took one of the y's out, plus, let's see, I got to use my calculator. What's 192 divided by 3? 64. But then again, remember, we took that y out of there. So it's kind of going back to what we did earlier in the notes. I've factored out as much as I could. And then now I look at what's left and see like, okay, hey, it's a two-termer. 64 is a little bit confusing because that's a perfect square as well as a perfect cube. But the problem is this is sum right here. The difference of cubes, difference of squares only works with squares, and this isn't a square, this isn't a square. So this is a sum of perfect cubes. So this 3y is just going to kind of linger here. We'll bring it down here to start. But what's the pattern? How does this work? This is going to factor as a two-termer, a binomial, and a trinomial. So I kind of set myself up. If I want to do the signs now, I can do that now if I want. Same, opposite, always positive. So I use the same sign, the opposite, always positive. So maybe you want to do that first because then, it reminds you that, hey, you need 5 different things. All right, what's the cube root of 27? 3 times 3 times 3. So I can show you how to do that on your calculator, but 3 times 3 times 3 is the cube root of 27, and the cube root of y to the third power is y. All right, so 3y, and then the cube root of 64. I know we kind of just wrote them on the previous page. So 4 times 4 times 4 is 64. So 3y plus 4. The cube root of each one gets written in both these positions. I square this first term, so 9y squared. So 9y squared. I square this last one. 4 times 4 is 16. I've got a space reserved for it. And then remember, this middle one is just this times this. So 4 times 3 is 12, and then the y, so 12y. So when that's all said and done, holy cow, look at that. That kind of seemingly not too bad, like two-term thing, polynomial, got factored down to this big, long polynomial. We broke it down into its factors. So again, that's going to take practice, but that's a pattern-based factoring. Let's keep it moving. Factor by grouping. Next one up. This is a new one for us. Although here's what I kind of referenced earlier. If you're counting your terms, all of a sudden this one jumps out as weird too, because what the heck? 1, 2, 3, 4. We've never, ever, ever seen a 4-term polynomial other than the one that we made ourselves. Remember this one? I'm going back to the first thing we did in the notes. Second thing. 1, 2, 3, 4. We created kind of a 4-term polynomial. So go figure, when I see a 1, 2, 3, 4-term polynomial, what are we going to do? we're going to group the first two terms together and the last two terms together and connect it to one that we kind of already know how to do, that we hopefully already know how to do. Okay, so that's what I mean by factor by grouping. We use it when we see four terms. It is every four-term polynomial factor like this? No, but for right now, that's the only way we know how to factor it. So if I'm asking you to factor something with four terms, chances are it's probably going to factor using this method. Okay, so I do that exact same thing. I look, okay, what can I take out of these first two? What's common here? I can take out an x squared. What would have to be left in the parentheses here? There'd have to be an x right here. Remember, I'm kind of redistributing. That'd be an x to the third, and then this is just going to be an x minus 3 over here, right? Because if I were to redistribute, I'd be at negative 3x squared. How does this work? Remember, you always just kind of set this up, say, oh, I got an x minus 3 right here. This must be x minus 3. And then we ask ourselves, what do I have to do to this to make it look like this? So obviously the numbers are getting smaller. I've taken out, let's see, the sign here changed, so this number must have been negative. And actually, this whole thing came out. Negative 16, if I take that out of there, yep, okay, I distribute. And then this is going to change this back. Negative 16 times negative 3 is positive 48. So we were able to take out a negative 16. And you can go back and watch it. How do we finish it? We say, all right, take the outside stuff and put it together in its own little binomial, x squared. Oh, this orange doesn't show up great. X squared minus 16. And then I just use one of these, x minus 3, and I say, yes, I feel so good. I'm so proud of myself. I did it. And I'm just being sarcastic and being mean because, oh, we're not quite done. So even on these ones where it's a factor by grouping, I still got to look at what's left. Is this always factorable? No. Like, you might get here and be done. But I'm seeing this and seeing, hey, this one's done. X minus 3 is x minus 3. I can't do anything else with that. But this one here that's got a difference of perfect square. This x squared minus 16 can go another round of, that's a pattern one. It's a two-termer, x plus 4. Whoops, not plus 4 again, but x minus 4, right? I'm breaking down this into x plus 4, x minus 4, and then the x minus 3 is just kind of along for the ride. So this part isn't necessarily new because we did that earlier on. It's from a quadratic section. The factor by grouping is the new part. Although, again, I would argue that it's not necessarily new because we did it with quadratic. So let's do another one. Just to kind of hopefully solidify this one here a little bit. It jumps out. It's four terms. The only thing I think of is, it's four terms. I only have one option. Put a group around the first two and the second two. Take out as much as we can here. So I can take out another x squared. What does that leave me with? X minus 2 in this one. We say, hey, I got to make this. This has to look identical to this one. X minus 2, x minus 2. So I'm going to have to take out a negative 9 here, because negative 9x, positive 18. I do that same. Like I said, I don't know if this is the best two examples in a row because we're left with something that's just like the last one. This can get factored again. It's another difference of squares pattern. So I know when we see this, we're like, oh, I always got to do this. It doesn't always work this way. It's just, it's a factoring lesson. So I guess I'm trying to get us some extra practice there. But that x squared, right, was another difference of squares. It was able to factor another round. But just be careful that you don't fall into like this always is factorable. If these aren't perfect squares, then it's not factorable anymore. So there we go. There's a factor by grouping. I know it was quick, but it's kind of the same thing twice in a row. All right, last, we're getting there. Last kind of new-ish technique. No, let's call it new because this is new. Factor something that's what we're calling in quadratic form. So I'm going to spread this out a little bit. The hard part here is these are two different types. And you say, what? How are these both the same? There's a two-term and a three-term. So here's the deal. We're still going to always want to look to see, can I take anything out? So I guess on this one, I'm seeing this as difference of 81's a perfect, 9 times 9 that's a perfect square. 4 times 4 is 16. X to the fourth is actually a perfect square. Now this would be one, let's see here. Can I take anything out of either of these? No, I don't think so. So it's a difference of squares pattern. What was that difference of squares pattern? Well, it's the square root of this one, so 4x. Now here's the only difference. What's the square root of x to the fourth? That's x squared times x squared. So I need a 4x squared, and what's the square root of 81? 9. 4x squared and a 9, and just like before, I need to remember that, hey, I need a plus and I need a minus. It's another one, as I look, we're seeing it for the third time, so you hopefully, and I guess it is a pretty common theme that I want to look at what's left. The directions still say, factor completely. I see another difference of 9's a perfect, 3 times 3, 2 times 2. So this is another 2x plus 3, 2x minus 3. Like this one can get factored again. This, however, so I guess it is kind of a good look for us here to see something that, although there's squares in it, can't get factored anymore. It has to be subtraction there. If it's not subtraction like this, then we just say, oh, no, we're done. Unless it was sum of cubes, but these are not perfect cubes. All right, so that one's a little bit, well, whatever. It's called quadratic form because it works just like difference of squares, even though it's technically like a fourth degree, which I would still argue is a difference of a perfect square. This next one here definitely looks weird. So it's a three-termer. How do we handle three-termers? We only know one way. It's traditional factoring. Now, again, that traditional factoring only works when it's a quadratic. Well, this is not quadratic, right? This is 12th degree. Holy cow. So let's kind of start where we should always start. We said look to factor out as much as possible. So we can take a 3 out of all these numbers, which is good. That's convenient. And I also recognize, hey, there's an m squared. Take as many m's out as possible. So I can take 2 m's out of everything. So what does that leave us? That leaves us at m to the 10th. Holy cow, m to the 10th. That's still really big. What's 54 divided by 3? 18 plus 18 m to the 5th. And then, let's see, 51, that's got to be 17. So we factored out. Hopefully at least that part is like, okay, yeah, I'm on board with that. I'm factoring out. What's the deal here? 10th degree? How the heck am I going to factor this? Let me ask you this. If this was m squared plus 18m plus 17, hopefully we would say, yeah, I know how to factor that. I need two numbers that multiply to 17 that add up to 18, right? Our quote-unquote traditional normal factoring. 17 times 1, or just 1, it doesn't matter. 1 times 17, 1 plus 17. Oh, that'd be m plus 1, m plus 17, right? That would be, I know that's not the problem, but it's close to it. I've seen m, an 18, and a 17. There's 3 terms. And it actually turns out that this process for finishing this one is exactly the same as this. So what's the recognition? What do I need to see? I need to see this exponent being twice as big as this one. Because if you think about it, what's going on here? This exponent 2 has always been twice as big as this one, which was 1. So in that case, with this 10 and this 5, I can treat this exactly like we did here. I need two numbers. Let's switch back to red. I need two numbers that multiply to 17 that add up to 18. Now I know we already know the numbers, 1 and 17, 1 and 17. So when I go to almost finish this, I'm going to say, all right, m, those two numbers I just came up with, and this is nice because it's a 1 there, m plus 1, m plus 17. But before I circle my answer, I say, wait a minute, hold on. This is like the quadratic factor. This was a 10th degree. So here's the thing. I just need to make sure that, oh, okay, these must have been m to the 5ths. And the quick check would be like refoil this, just in your head. If I were to refoil this, m to the 5th times m to the 5th, I need to get back to m to the 10th. And then I'm going to end up with a 17m to the 5th plus a 1m to the 5th. There's where your 18 is going to come from, and then your 17 there. So you kind of treat it just like it was a quadratic, even though it's not technically, second degree. So there we go. Kind of factoring as if it were a traditional factor after factoring something out, using our traditional method. Okay. Whoops, didn't mean to go that far. Let's take a look at a couple. Both of these review that same concept. So, and that you're seeing them both here. This first one, I'm looking at this. Are these perfect squares? 9 times 9, x squared times x squared, and 256. Yeah, that's a perfect square. That's 16 times 16, and it's difference. That's kind of a big deal there. Difference of perfect squares. So this is one that I'm ready to jump to what I think may be my final answer. We said 9x squared, and then 16, and then 9x squared, and 16. And just remember that I need a plus and a minus. For like the 5th time in a row. This one's done. 9x squared plus 16. But then I'm seeing this difference of a perfect square again. This one's got like another round that we got to hit. So the square root of 9 is 3x, and the square root of 16 is 4. 3x and 4 plus minus. So yeah, very similar to the one we just looked at. Again, I hesitate a little bit. Maybe you got to rethink the examples. That doesn't always happen. So just be aware that if you end up with something, I just feel like sometimes I almost trick you into thinking like, hey, there's always like 2 or 3, 4 rounds of factoring, when maybe there is only that one. Let's look at B here. So similar to the one that we just finished up, the previous example. Take out as much as we can, and it's actually similar in the sense that everything's divisible by 3. I can take out, let's see, 3 total y's. So this is going to leave me with a y to the 4th. Let's see, I divided this by 3, so this is going to be a 5y squared. And then this is going to have to be a 6, just a 6, right? Because we took all the y's. So, I kind of look at it and I think, okay, can I factor this? And maybe I can, maybe I can't. Do I have the chance to treat it like a quadratic? It's a 3-termer. Is this twice as big as this? Yeah, 4th, 2nd. Okay, so I'm going to at least try to come up with 2 numbers that multiply to 6 that add up to -5. And this one can kind of be tricky. So I'm thinking 3 and 2. Let's see, can I make it work? Or 6 and 1 sometime, with the 6 and the 5. Is it 6 and 1 or is it 3 and 2? Let's take a look. If it's -3 and -2, yeah, I think that would work. So -3 times -2 is +6. -3 plus -2 is -5. So my finish then is 3, this 3y to the 3rd that was already just hanging out there. And then we go right to y minus 3, y minus 2. I'm just using these numbers. And then just don't forget to look back and say, oh, yeah, that's right. It wasn't quite quadratic. These were, let's see, these would have to be second. When in doubt, it's always going to be this one right here. But just kind of think, what would I have to multiply? Y squared times y squared is going to get me that y 4th. I almost forgot to look. It's close. Y squared minus 3, y squared minus 2. And I should actually go back and look at that last one because I guess I didn't look there. These were pluses, so that's why it didn't jump out at me. But these were both close to being factorable again. If this was y squared minus 4, right, we could go difference of squares again. It wasn't, so, but I just wanted to at least, it scared me for a second that I forgot to look at the last one. All right, that's the majority of the new stuff. I know you're thinking like, what? There's still a whole bunch of slides left here. We can use these concepts to help us solve equations. So hopefully at this point, well, let's see here. Let's do it. Let's talk through it. But it's still factoring to help now solve the equation. These all got, every answer we circled was just a big box around a bunch of x's and x plus, Whereas here, when it says solve the equation or find the real number solutions, we're going to factor it. We're just going to take it one step further. So let's take a look. All right, we got to get it equal to 0. So the first step would be to get equal to 0 if you're not already. So x to the 4th, I'm going to bring this over, minus 10x squared plus 9 is equal to 0. All right. How do I solve that? I can't use the quadratic formula because this isn't second degree. So I'm saying, all right, let's factor this. Can I come up with, it's a 3-termer, so I'm thinking traditional. I'm looking for two numbers that multiply to 9 that add up to -10. Let's see. -9 and -1, -9, -1. Sweet. So x minus 9, x minus 1. Oh, don't forget, it was second degree here, so I got to put a little squared on both of these. Oh, and this one's so mean. These both factor. Again, these are both difference of squares patterns. Oops, and don't forget this part either, that we were equal to 0. That was kind of the whole focus of us doing this one. Difference of perfect squares. So this is x plus 3, x minus 3. That's what this one goes to. Let's change colors here because, and then this x, people don't recognize this one because the 1, it doesn't jump out as you. It's like, oh, 9, that's this, that's 3. But this is actually a perfect square, 1 times 1. So x plus 1, x minus 1 equal to 0. So both of those ended up factoring again. Here's the finish then. We did this in chapter 3 a lot, where once we got everything factored, which that's kind of an if. I mean, if we can get to this spot, that should hopefully be a win for us. But then instead of just circling this and saying, hey, I'm factored, I'm done now, remember it was asking for what are the solutions. So we finish this with, oh, x equals, and I go one by one and say, what makes this equal to 0? Just ignoring all this other stuff and just, whoops, I didn't mean to do that. And asking, what makes x plus 3 equal to 0? Oh, -3. What makes x minus 3 equal to 0? +3. What makes x plus 1 equal to 0? -1. And then x minus 1, that would be 1. So I end up finishing it. And we could do that for any one of these. We could go back and say, oh, if this was part of a solution, it would be, equal to 0. And then we'd say, all right, set this equal to 0, set this equal to 0, set this equal to 0. And some of those are harder than others. We'll look at maybe a couple here that force us to do that a little bit, but that's kind of the last step of the process there is find the solutions, set them equal to 0, and solve. All right. I know we're almost there. Just stay with me here a little bit. So this last part here, this what's called the factor theorem. We didn't see this a ton when we were doing the long division or the synthetic division, but I think it did happen a couple times when we divide polynomials and we get 0 as a remainder of it. Most of the time we got remainders. But what would it mean if you divide by something, 80 divided by 4? Well, 4 goes into 80 evenly. It goes in there 20 times. That means 4 is a factor of 80. So for us, when we divide a polynomial and we get 0 for a remainder, it means that, well, what we divided by must have been a factor of the polynomial. That's kind of the big takeaway. So make sure you set up a section. It's called the factor theorem. Basically, if we divide a polynomial by a number k, then that factor, then x minus k, must be a factor of the polynomial. Okay, as long as we get 0 for a remainder, that's kind of a big deal as well. Let's take a look here. So what am I asking you to do? Darn it, I wish I could. Let's do the first one here. So for part A, it's asking us, is x minus 2 a factor of this one? So basically what we need to do is divide this by x minus 2 and then see, do we get a remainder? What's the remainder? If the remainder is 0, then we would say, yep, this has to be a factor because it went in there evenly. If you get a remainder, you say, no, it's not a factor. It didn't go in there evenly. So how do I want to do this? Do I want to do long division? And the answer is resoundingly no. I don't want to do long division. That stunk. Big, long process. So we're going to use synthetic division. So let's use the 1, the 2, and the -4. Maybe I can squeeze it left and right here with A and B. We'll do B separately, but so 1, 2, -4. I got to make sure, just like we did, we're not changing anything. I just want to make sure that we recognize that I got to use 2 right here, right? 2, I want to check, does 2 go in here? So I got to use whatever's going to make this equal to 0. So I check it. I drop down the 1. Remember how this works? The 1 drops down. 2 times 1 is 2. 2 plus 2 is 4. 4 times 2 is 8. Negative 4 plus 8 is 4. You say, what? Not that we did anything wrong. It's just, no. Let's just say not a factor. This did not go in there evenly. Okay. And that's all it's asking. For part B, just let's double check this here because I know I kind of see what's happening here. I need a little bit more space because I'm going to use that same process. 3, so fourth, 15, negative 1. Uh-oh, we're skipping over one here. That's easy to miss. All right, so I skipped over the first degree spot, so I left a 0 for it. All right, and then we're checking. All right, I want to check, does negative 5, when I divide by this, I'd actually be using a negative 5 right here. So let's do it. Drop down the 3. 5, negative 5 times 3 is negative 15. Now, just this right here is 0. That doesn't mean anything. Like, we got to get to the end. So negative 5, and it doesn't mean that it's going to be zeros the rest of the way either, because we're going to add. Negative 5 times 0 is 0. Negative 1 plus 0 is negative 1. Negative 5 times negative 1 is 5. 0 plus 5 is 5. And then 5 times negative 5 is negative 25. Look at that. I got a 0. All we're really interested in is this right here. Hey, it's 0. Sweet. Yeah. X plus 5 is a factor. It means that once we divided this by this, it went in there evenly. And we'll take this down the road in the next chapter. We'll take this further. But for right now, that's kind of what we need to be able to do and recognize. Okay, so we can use that. Okay, so now it's basically telling us that, hey, you know what? This is a factor. This goes into this. And you're like, okay, that's awesome. Sweet. But we can use that information to help us factor this completely. So follow with me here on this one, and then we'll do one last. Oh, I got 2 example 7s. I'll keep my fingers crossed. Maybe they're both the same. This is probably example 8. We'll see. So use synthetic division. It's basically saying, okay, hey, use synthetic division. 2, negative 11, 3, and 36. Divide by, in this case, 3. Use synthetic division with 3. I know what's going to happen. There better be a 0 for a remainder here. Otherwise, something's screwed up. Because it told us that given that this is a factor, this goes in here. So let's confirm it. 2, 3 times 2 is 6, negative 5. Let's see, negative 15, negative 12, and then 3 times negative 12 is negative 36. Yeah, look at that. Fortune teller. Okay, we just did that. So what? Yeah, all it did was confirm that this was a factor. So combining that concept with, remember, how does this work? If I was actually doing the long division, how does this work now? This is a 2. We drop a degree, x squared minus 5x, and then minus 12. So we went from something that was 3rd degree, we divided it by one of its factors, down to a 2nd degree. We have skills and some tools that we can use on 2nd degree stuff. Now, this isn't a super easy factor, but basically we dropped it down a degree using this information and say, hey, you know what? Let's finish by factoring this. We've come full circle here. Let's finish this one. This is one of those traditional factors that are kind of the long factors. So I need 2 numbers that multiply, oh no, to negative 24, that add up to negative 5. Hopefully at this point we're like, oh geez, I'm burnt out. But it's at least like, okay, I know how to do it. That's kind of the bigger picture. 8 times 3, 24. 8 plus 3. I just need to make, let's see, the 8 negative, right? Remember, we got to come all the way back and rewrite this original 2x squared minus 8x plus 3x minus 12. We've kind of created this factor by grouping. So I'm going to group the first 2, group the second 2. What can I take out of here? A 2x. This is going to have to be an x minus 4. Remember, we need to make this one look identical. So x minus 4. What has to come out of here? A 3. So then we put it all together and say, oh, 2x. Remember, this outside stuff gets put together. 2x plus 3. We just use one of these, x minus 4. And I know it's easy to forget. And if you got here, I'd say, yeah, you did a really good job, and I'd probably give you full credit. Just this was one of the factors of this original one. So, I mean, what was the directions originally? Factor this. Okay, break it into its factors, given that this was one of the factors. So I think it's also easy to do. Just tack that freebie onto the end. Oh, x minus 3. It's an x. So for right now, you may be asking yourself, like, that was really like convenient. Like, why did they just say, like, hey, this was a factor? We're eventually going to take that away and say, hey, just factor this completely, and we'll get there with that. But use a factor to help you finish factoring it is kind of what I would call this section. Okay, let's see. Did I screw up and make 2 example 7s, or is this a new one? Oh, it is one more. So it is worth doing here because it's a little bit different. Last one, I promise. I don't have them all out of slides. All right, it says 1, 0 of this function is right here. Find the other zeros. All right. So we're going to start out with synthetic. Okay, 1, 4, negative 15, negative 18. Now remember, the way it works like this, when it says one of my zeros, it's actually saying this is one of my solutions. Remember, this is kind of saying, hey, we're building in answers are a little bit different. So x equals negative 1. That's one of my answers already. It's kind of saying, here's one of the answers. Use this answer to help you find the other answers. You know, as if we were solving this equation where this was equal to 0. So we want to make sure we use negative 1 out there. All right, we saw that in the last section, and it seemed like most people did okay with it. Drop this down 1. We're hoping this better be 0. Let's see here. So 3, negative 3, negative 18, positive 18. Sure. Now, be careful there, just because these numbers do matter to us, right? Because now, just like the last one, we're going to use this as we're dropping a degree. We went from 3rd degree down to 2nd degree, plus 3x, and then minus 18. And we're equal to 0 because this was originally equal to 0 because we were finding the zeros. At least on the finish here, it's one that we can say traditional, in the sense that I need 2 numbers that multiply to 18 that add up to 3 that aren't. This isn't that brutal case because that's a 1. Okay, so what do we got? 9 and 2, no. 6 and 3, can we make that work? 6 and 3, 6 and 3. Yeah, I think so. 6 times negative 3, 6 plus negative 3, sure. So x plus 6, x minus 3. Just don't forget, I almost did myself, we're equal to 0 here. We want to finish this with the other solution. So x, what would make each of these equal to 0? Negative 6 and positive 3. So I finish it. Where before we were just factoring, now it says, all right, find the zeros. So if I was building that list from the get-go, it told us one of the answers was negative 1. Find the other zeros. Well, we just came up with them, negative 6 and 3. Oh, my hand is cramping up here, and I bet yours is too. Yeah, that's kind of a long lesson, no doubt about it. The reason I spent more time with it, like I said at the beginning, is depending on your level of comfort with factoring, this could be a really, really tough lesson. I think it is, regardless whether you were really strong with factoring or quadratics, or you were weak with factoring quadratics. But it's especially tough if you don't remember anything about factoring from the previous chapter. So it looks so innocent at the start here. Two skills. Oh, sweet. Factor completely and use the factor theorem. Well, yeah, again, that's kind of a loaded big idea, in that if you don't remember anything about factoring from the last chapter, we had a lot to go over there. So that's definitely it. 4 4 is in the books. That's actually the end of the part 1 of the chapter. So we'll kind of wrap the chapter up, take a break, do an assessment, and then move forward from there. So yeah, let's call it enough's enough. We are officially done with lesson 4.4. I'll see you in future lessons.